Okay. This is trying to finish up Chapter 7, oh my goodness, I don't know how many. I've been trying to do this several times, and I keep running out of time each and every time, so I'm hoping this will work. Okay, the last section, I figure, it's not something we need to talk about in class. We can do that. You guys can look at this on your own, and even though you have the completed ideas, the completed set of notes, I felt it was kind of important to talk a little bit about the history of the periodic table, periodic trends, things like that. Pretty much Mendeleev is given the credit for our periodic chart that we have today. Even though there were other guys involved in it, Mendeleev was pretty much the one who did things. Now we have to talk a little bit about the Aufbau principle, okay? And basically the idea is this. When you keep adding protons to the nucleus, okay, the electrons are also similarly added, kind of like the hydrogen-like orbitals. And what does that mean? Well, you look at something here that there's a certain order that needs to be filled in. And so if we look at oxygen as an atom, okay, we have 16 electrons, how many electrons? No, 8 electrons, I'm sorry. Okay, and you're going to have 2 in level 1, sublevel S, 2 in level 2, sublevel S, and then 4 in level 2, sublevel P. That's the general idea for that. In Hund's rule, we look at the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of same energy orbitals. Again, I'm not going to worry too much about Hund's rule, okay? But I do want to look at the orbital diagram because I think that's a very key thing for notation. When we look at an orbital diagram, we look at something like this, where we look at oxygen that has 8 electrons. Okay, so this is our standard notation, but here we have these where we're filling in the arrows. So for 1s we have a box, 2s we have another box, and then 2p we've got 3 boxes together. Now, the arrows themselves, they represent the electrons. Now, the arrow going up and the arrow going down are the opposite spins that the electrons have of each other. Okay, so 1s and 2s, they're filled automatically. When you look at 2p, you notice that we didn't put in 1, 2, 3, 4. It's 1, 2, 3, then you go back for the 4th one. It's sort of like the Monopoly game. If you buy 3 lands of the same color and you buy 4 houses, you can't put all 4 houses on one land. You have to spread it out evenly. And that's how I liken this idea to Monopoly as a set. So you have to spread out the electrons there. Valence electrons, this is kind of fairly straightforward. You know it. It's the outermost principal quantum level of the atom, okay, the outermost level of electrons. So when we look here, for example, here's neon. Okay, we're only interested in what's at the highest level, and there it is, level 2. So how many do we have in level 2? 2 plus 6 gets us 8 electrons, which, guess what, neon is a noble gas, so we don't have to worry about that. Okay? All right. So here, this chart shows you what is being filled out as far as the highest orbital, which might explain why, if you go along this group here, you have 1 valence electron, and here you have 2 valence electrons. When you come over to here, okay, your maximum level, all right, you'll see that as you're going down the periods, okay, your P's and D's, you know, that they are also matching. Okay, as you go down a period, it increases. All right. Moving on. Okay, let's quickly look at the expected electron configurations. We look at sulfur. Sulfur has 16 electrons. And this is the normal standard notation for sulfur, okay? So when we look at how many valence electrons does sulfur have, well, we can look at level 3 here, and there's 2 and 4, or 6 electrons for sulfur. Now you notice there's or, Ne, and then 3s2 and 3p4. What's up with the Ne? Well, the Ne is shorthand. It's basically saying, instead of writing out 1s2, 2s2, 2p6, which happens to be the electron configuration for neon, we write the bracket and neon in there, and that saves us some of the shorthand. So when we look at Ba, barium, it has the configuration of xenon, and then it has a 6s2, which, if you look at the periodic table here, here's barium in column 2. So you look at it, you see 1, 2, 3, 4, 5, 6, level 6. Okay, you have xenon on the other end, which is the closest noble gas. So there's the barium, 1, 2. So we would see xenon, and then 6s1, 6s2. So that's why it looks exactly like this. All right. Okay, gotta keep going. We got to look at periodic trends very quickly, and there's a few of those that we're going to go through. And like I said, this is stuff you can cover on your own time, but I'll talk to you guys a little bit about it. Ionization energy, the idea is very simple. How much energy does it take to rip an electron from an atom that's either a gas or it's an ion? That's pretty much it. So we look at magnesium, for example. Ripping out the first electron in magnesium, it's about 735 kilojoules for 1 mole. That's the first IE, or first ionization energy. If you look at the second electron that needs to be ripped out, notice that it takes some more energy in order to do that. Okay, but now look at the third one. Taking out the third electron, look at the jump between 1445 and 7730. That's a lot. Well, what's happening? Well, remember, when you're looking, there's something about core electrons. Core electrons are closer to the nucleus. The nucleus is going to hold on a little bit more tightly, because typically when you look at magnesium, if we look on the periodic chart for magnesium, okay, we have it up here. Typically it has a charge of +2. Okay, so taking out 2 electrons isn't a big deal because it has that full outer shell of electrons once those first 2 have taken off, right? Okay, well, what's going on then? Well, you're going to put in a lot more effort to rip out that third electron, because now it's a core electron, it's a lot closer. Okay? So it takes a lot more effort to go in there. Okay. So what about the trends? If we're going from left to right, the first ionization energy increases. Well, how come? Well, keep in mind, one, the atom is getting larger as you're going across from left to right. You're getting more protons added, but you're also getting extra electrons added. Okay? Electrons added in the same principal quantum level, that means level 2 or level 3 or level 1, do not completely shield the increasing nuclear charge caused by the added protons. And it kind of makes it harder, okay, for the electrons to go through. So if you're looking at 2s2, then 2p1, okay, it makes it, compared to the next atom, which would have 2s2, 2p2, it kind of makes it a little bit harder to take that out. The other thing is, the electrons in the same principal quantum level are generally more strongly bound from the left to the right of the periodic table. There is that as well. So in general, here's another trend. So we looked at going across a period. If we're going top to bottom, what's going on is, as you're going from top to bottom, that first ionization energy actually goes down. Okay? And why is that? Well, it has to do with when you go down a column, the atom gets larger in size. So that means the first electron is further away from the nucleus, and it's a lot easier to remove that one electron away from that nucleus of that atom. Okay, so that's basically the idea. And we look at this here. Here is the amount of energy, ionization energy that's needed compared to the atomic number. If we look at period 2 and 3 and 4 and 5 and 6, you kind of notice, if you look at helium, neon, argon, krypton, xenon, and radon, if you notice, they're all very relatively high compared to the other atoms in this same period. Well, why is that? Remember, they're noble gases, so it's fully packed, fully tight. But look at helium and compare it to argon. Okay, well, helium is going to have a higher, it's going to have a higher value for that first ionization energy. Why? Because, well, you know what? That first electron is right next to the helium's nucleus, very tightly held on, okay, compared to neon, which is in level 2. Okay, so here it's in level 1, here it's in level 2. So that's why. All right. So why is it the graph of ionization energy versus atomic number across a row isn't linear? If you look at this, it's not exactly linear, is it? It's kind of jagged, going up and down like this. And it has to do with that the electrons themselves, that they repulse each other. Okay? That's pretty much it. And there are some exceptions. I'm not going to worry about the exceptions. I'm not going to do that with you guys. All right, so when we look here, concept check, which atom would we require more energy to remove an electron and why? Well, Cl would be it. That's because the electron is more tightly bound due to the increase in effective nuclear charge. Remember, sodium has got that one electron in its outermost layer. It's not a big deal for it to lose it, okay? Whereas chlorine, it's got 7. Okay, and that's going to be harder. You have to put more energy into it. Now, which atom would require more energy to remove an electron and why? Lithium or cesium? The lithium. And that's because the outer electron is closer to the nucleus of lithium than it is to the cesium. If we were to go and look at the sides here, okay, here's cesium and here's lithium. Okay, so lithium, ripping out that first electron, it's really close to the nucleus because it's only got 3 electrons. Cesium has got 55 electrons. Ripping out the first one isn't really a big deal compared to the lithium because the lithium, the electron is closer to the nucleus. So that's a fairly important concept. Now, which has the larger second ionization energy and why? Okay, lithium or beryllium? Now, beryllium is number 4, element number 4. Lithium is element number 3. Lithium, to rip out the second electron, now you're looking at level 1, because lithium has a 1s2, 2s1. Taking out the first one, all right, now you're taking the second one, which is a core electron. It's right next to the nucleus. That would be a big deal, okay? It's smaller and it's a lot tighter, it's a lot more packed compared to beryllium, okay? So when we look at this just gives you an idea of the, ionization energy. How much energy does it take to rip the electrons out, okay? And you kind of notice for something like argon, look when you have to take out the 7th electron, how much energy you have to put into it. That's a lot. Really. And then when you start looking at core electrons, like of sulfur, 27,000. Oof. All right. Electron affinity. We've got to move on. There's going to be an energy change that's associated with adding an electron to a gaseous item. Okay? Think about the word affinity. What does affinity mean? It's something that you like, okay, or you're a natural at it. Okay, so electron energy changes associated with adding an electron to a gaseous atom, sorry. So here's X of our gas compared to, plus an electron, and then we got X with a negative charge. When you go from left to right, the electron affinity becomes a little bit more negative, okay? And in general, the electron affinity becomes more positive if you're going down the group. atomic radius, like I said, I'm running out of time here. In general, atomic radius, as you are going from left to right across a period, the radius actually decreases a little bit. So what's happening? Well, you've got more protons added in there. With more protons, that puts a little bit more of a positive charge, and opposites attract, so it kind of pulls in the electrons just a little bit. They're a little bit drawn closer to the nucleus, and it cuts down on the size of the atom. Now, if you are going down a column, then the atomic radius actually goes up, and that has to do with every level that you go down a column, okay, a group, you've got another layer of electrons that are added. So the the size of the atom actually gets larger, okay, in the process. This is kind of a review from Chem, and here's some examples of that, atomic radii for some of the selected atoms out there. So when we look, which one would we expect it to be the larger atom, and why? Well, it's going to be sodium compared to chlorine. Okay, now it's going to become, sodium is the larger atom because the electrons, they're not bound as tightly because there is more of a smaller effective nuclear charge. In other words, that positive nucleus isn't putting out the same amount of power, that same amount of attractiveness compared to the chlorine. And remember, sodium is more likely to lose its electron compared to chlorine. So there's a kind of a relationship that's there. Now, which would we expect it to be the larger atom, lithium or cesium? Well, if you look at the chart here, here's lithium and here's cesium. As you're going down the chart, okay, each row that you're coming, you got another layer of electrons added. So yeah, cesium is going to be definitely bigger in size than lithium. Okay. So now, periodic trends and atomic properties as we're winding down. Which is larger, the hydrogen 1s orbital or the lithium 1s orbital? Okay. Well, it's going to be the hydrogen 1s orbital. You said, wait a minute, aren't all 1s orbitals the same? No, they're not. They may be level 1, sublevel s, the shape of the cloud that the electrons will hang in, but they're not all the same size. And that has to do with the hydrogen is going to be larger in size because the electrons are not as tightly bound to the nucleus of the hydrogen compared to the lithium. Lithium has more of an effect on its electrons than the hydrogen does. So that's why hydrogen would be larger. Now, which one would you expect to be lower in energy? Is it the hydrogen or the lithium? The lithium is going to be lower in energy. And again, that's because the electrons are closer to the nucleus as a result. Okay, moving on here. Here's again atomic radius of a nonmetal and metals for comparison. All right, now arrange the elements oxygen, fluorine, and sulfur according to increasing ionization energy and atomic size. This you would have to be familiar with the periodic table trends, and I'll see about getting you guys a packet for that so you can go and look at it. But you should be able to do this. You should know the periodic table trends on that. Final thoughts as we're wrapping up here. Okay. Think about this, guys. I've always made a big deal about valence electrons. Number and type of valence electrons primarily determine the atom's chemistry. Okay? We can look at the electron configurations based on the organization of the periodic table. And of course, certain groups in the periodic table have special names like the halogens, the noble gases, the alkali metals, the alkaline earth metals, as we go through here. And those four you should be able to know. Now you should know about transition elements as well. Lanthanides and actinides, yeah, I wouldn't place as an important. I'd rather have you guys know these five. That's a far more important thing to do as we go through here. Metals versus non-metals, in case you kind of notice here, a lot of the elements are metals. And then you have non-metals.